Okay. Hello. Once you get in the room, if you guys could say hi, that'd be awesome. And if you are here, there's one person who's, oh, hey, how's it going there? Um, hey, Isaiah, good to see you. Hi, Anessa. Could one of you guys post in your class chat on WhatsApp that we're on because some people might not have seen the message? That would be lovely. Thank you. Thanks, Isaiah. Hi, Dr. Feldmarsh. Yeah, I'm actually in the classroom W301 at JFK. Wanted to try out how it works from here, and also I missed meeting Mr. Weiss. He wanted to meet with me for a meeting, so I'll meet with him later. But otherwise, I'm not planning on being here every day. But today I'm here, and I'll be here maybe on Wednesday. I have to be here on Wednesday as well. So, is the connection okay? Because I'm running this over the school network, and ironically, it seems to me the school network is less reliable than my home Wi-Fi and DSL, which is sad. But from here, it looks like I'm doing okay. But are you guys able to see it? Is the connection okay? It's okay. Fine. Okay. Cool. Great. Hi, Eve is Lillian, right? Good. Okay, sweet. Let me see. Theo, Liam, Matthias, Cassidy, Lauren, not here. Correct? So we have 4. That's not great. Let's see. We still have a minute till 9 o'clock, so maybe people will show up. Did you guys play around with the circuit building kit on FET? Did somebody try that out? I mean, I know you tried it, but did you like start building circuits? I think Feldmarsh mentioned last time that he was already kind of messing around with it. Did people build some circuits and any report back? Hi, Matthias. Hey, Liam. A bit, Inessa? Okay. Is it easy to use the FET circuits thingamajig? Okay. Yeah, works okay. Cool. Thank you. Good. Glad to know that you made a lot of circuits, and that you were able to do that. Yeah. Okie dokie. Cool. Cool. Okay, we have still missing Theo, Cassidy, and Lauren. Any information about those? I am at school, Liam. I have come back to school for today, this morning at least, just to try it out. I'm on the school network, and we're transitioning slowly into opening school for some of our students. 10th graders are supposed to be back in school next week, just for German, English, and math. And the graduation tests, the Abiturklausuren, are beginning this week as well. So hi Cassidy. I wanted to come by and see how it works over here, try out the network, see if my setup over here works as well, and kind of see if I do have to come back here in terms of meeting with other classes, like I have 2 10th grade classes, for example, whether in between I can do these YouTube live streams from here, whether that works okay. So we'll try that out. For now, we are on YouTube. We might try out Zoom at some point. I think we mentioned that. But today we'll be on YouTube still, and it's easier to record it on YouTube, especially if we don't have to worry about your faces being preserved on the internet forever, which is obviously a potential Datenschutzproblem. So for now, for today at least, we'll stick on YouTube, and then next week we'll see. Cassidy is here. Thank you. And Lauren and Theo are not here, but I think with 7 from 9, we're pretty good. So what I wanted to do hey, Lauren. Cool. Lauren's here. Nice. So it's just Theo, I think. So that's pretty good attendance. What I wanted to do was talk a little bit more about circuits, because I think we were a little bit rushed to get everything done in terms of talking about series circuits and parallel circuits. And I just wanted to take a little bit of time to review that. You guys are working on the lab this week and should complete that. I think it's due on Friday. I don't have it in front of me right now, but the deadline's coming up. And so I wanted to make sure you guys have a sense for how that works. Okay? So, and foolishly, I thought it might be interesting to try to see what happens when we combine a series circuit and a parallel circuit together. Okay, so let's take a look at the board over here. I've got me chalk, and we're going to draw. Let me see, where are we? So make sure we're on the board. Okay, here I'm still in the picture. Okay, good. So I'm going to draw lines in big so you can see it. That seems to be showing up. Okay, so we have some kind of, that's showing up over there, right at the edge, right? Okay, so there's the power source of some type, and we've got to connect it over here. All right, good. And we're gonna put a resistor here. We're gonna put 2 resistors down here. Still in the diagram, and then go here, and there. Okay, and we'll put some values on here. We'll say that this thing right over here is the power source has a voltage of 12 volts. Okay, we'll say this resistor right here, we'll call this R1, and R1 is 4 ohms. And then we have R2 here, and R2 is 3 ohms. And then we have a third resistor here, that is 6 ohms. Okay, all right, I don't like how the light's working here. When I go next to it, it's kind of hard to see. Can you guys see the circuit? The image is not that great. Bring it a little closer. I go out of the way, does it kind of focus on it a little? It's a little easier on the whiteboard, but I'm pressing really hard to help you see it. So I'm going to ask you a question. You look at this circuit, you see the power source here, okay? And then you have one resistor here, and then you have another couple of resistors down here. Okay, cool. So the question I have for you guys is this. When you look at this whole, okay, if you look at the whole circuit, is this, I'm going to step over here. Is this, or maybe that works better with the lighting then. Is this circuit overall a parallel circuit or a series circuit? So if you look at this circuit, is it parallel or is it series? And just type think about it for a second. Okay, I like Feldmarsh's answer. I'd forgotten. People have an opinion? Liam? Matthias? Isaiah? Any opinions? S or P? Just type something in. Just guess. I don't know. If you don't know, just guess. Serious. Okay. I think most of you are tending towards serious. Figure out why that's correct. Okay. And to understand why that's correct, let's think about the current. Because if you want to analyze a circuit, you should always think like the current or the charge. So if you're on this mountain, right, you've been lifted up by the ski lift to the top of the mountain. Okay. If you've been lifted up to the top of the mountain, you then are faced with a choice or no choice. When you look at this purple, if you're looking at that and say, okay, if we think about these two paths, they're really next to each other on two slopes that are next to each other. But what's going on here? Okay, so I'll slow down, Inessa. So okay, just let's see a second if it settles down, hopefully. Okay, so the charge or the skiers have to go through the orange element and then through the purple element. There is no choice. So this is a series circuit that has the orange and then the purple in series after each other. If we were to draw this as our ski resort analogy, it would look like this. Ah, shiitake. I'm gonna make that a little bit prettier. It's kind of tight. Oh man, that's not a very good drawing, is it? Hang on. I'm going to do something here. It's hard to see, so I'm going to get closer, okay? So what we have here, stay, okay, is that you first have to come through the top resistor R1, and to make it down the rest of the hill, you have a choice of going through R2 and R3. But it doesn't change the fact that you first have to go through the orange part of the slope, and then you have to go down the purple hill. But on the purple hill, you've got two paths to come down it. Maybe it's a harder run and an easier run there. Okay, now I haven't heard anything from you guys in a little while, so say hello to make me feel like I'm not alone, or maybe I am alone. That's okay too. Then I'll just have to reconnect. Are you guys still there? Hello? Hey, hello? Okay. Did you guys follow? Yes, hello. Did you guys follow my explanation of I'm not there? Ha ha ha. That's hilarious. Okay, so are you did you guys follow my explanation why this would be considered a series circuit, meaning you first have to come down the orange hill and then you have to come down the purple hill, but on the purple hill you have a choice which path to take, which run to take, but you have to in series go through the orange and then through the purple. Does that make sense? Good. Good. Okay. Okay. So what I'm going to do now, I'm going to change my plan a little bit. Just because um, I'm going to change my plan a little bit because I want to make sure you understand the difference between a parallel and a series circuit. So I'll give you another one to think about, and I think you're like kind of, probably already guessing what kind of circuit this will be based on the previous question we just answered. But here we go. So I'm over here. I got room. Okay, so here's my power supply again. We're going to say delta V is 12 volts. And I'm on the board. I am. And I'm going to go over here. So this time we're going to go a little bit different. We got R1 here. I'm going to say R1 is 3 ohms. Then we've got R2 here, and R2 is 4 ohms. And then R3 here is, oops, sorry, 2 ohms. That's what I have to do. 2 ohms. Okay, so we have a new circuit here. It looks a little bit different than the last one. And now I'd like to ask you the question, is this a series circuit or a parallel circuit? Okay, so same question again. Series or parallel? Okay, so which one is it in this case? Just type in SRP. Let's go. Okay, everybody's shooting a parallel. That makes sense. It is parallel. And why is it parallel? It's parallel because we can really consider these two together and this one alone. And if you look at this, you have a circuit where the purple, the purple and the orange are two options that you would have as a skier when you get to the top of your mountain. So when you get to the top of the hill, we can again do an analogy. I'm going to squeeze it down here. So this time, when you get to the top, you immediately need to choose. And when you choose, you can either go down the run that takes you right to the bottom. There it is. Take it right to the bottom. Make it, yeah, that's fine. Good. There we go. Or you might have an option where you come down one run and then you have a little plateau there. It's going to be a little bit drawy, complicated maybe. There you go. Oh, yeah. And then you go down a second run. And at the bottom, you're again at the same place. And then you can get back over here to get back on your ski lift, which will lift you to the top. There we go. That's showing up? Okay, that's showing up. So then we have here a combination. The purple one is this one. There's an orange hill, which has just one to come down, or a purple hill where you only have to go through one of these, or you have the orange combination. And the orange combination, you're still making it from the top of all the way to the mountain, all the way to the bottom, but on that path, you go in down two in series. Okay? So let's take a look at this and think about how much current flows through each of those elements. Okay, so let's think about how much current flows through each of these elements. So to answer that question, here's the first question I have for you, which is you've got this 3 ohm resistor. You've got this 3 ohm resistor here, right? If I were to apply a voltmeter here to measure the voltage across R1, the voltage across R1, how big would that measurement be? What is the voltage across voltmeter 1 in this case? So just type the answer in the chat. There's a question mark. What's delta V1? What's the reading on the voltmeter to measure the voltage across the 3 ohm resistor? Okay, you guys are still there, right? good guess. Wrong, Feldmarsh. Nice. Okay. Let's take a step back and riddle me this. Okay? So, voltage difference, potential difference, delta V, what a voltmeter reads is voltage is a height difference. Okay? So, a voltmeter would measure how much height difference there is between the two sides. Okay? So let's take a look. Our power source is the ski lift that lifts you up. How high does our power source lift you up? How many meters does our ski lift you up? It lifts you up 12 volts. Okay, of course, ski lifts are actually meters, but for a power source, it lifts you up a certain number of volts. It lifts you up 12 volts. So the ski lift over here lifts you up 1,200 meters. Okay, we're getting there, just a second. So the power source lifted you up 12, mountain, all the way to the bottom of the mountain, top of the mountain to the bottom mountain, or is the total distance you drop less than the total distance that you were lifted up? Is the distance you drop in the purple resistor, in the 3 ohm resistor, the same vertical distance that you were lifted up by the ski lift? Yes, I think it does actually. We could say, okay, we know that if we were to measure V total is 12 volts. Yes, yes, yes. Okay, so the ski lift lifted you up 12 volts. Okay, and now when you come down the purple run, it takes you all the way to the bottom, so you drop down the total vertical distance that you were lifted by the ski lift when you pass down the purple side. So therefore, V1 needs to be, delta V1 needs to be 12 volts. Okay, oh, good. We're getting this. Fantastic. Good. So we have 12 volts that you drop. You go down 12 volts. So we now know delta V1 is 12 volts. And we know the resistance of R1 is 3 ohms. So knowing the voltage and knowing the resistance, we can get the current that passes through the purple branch. Okay, that would be R1, I1, sorry. I1. Okay, so I1 passes through resistor R1, that's the current, and it's dropping a voltage of 12 volts, and it passes through 3 ohms of resistance. How much current is I1? What is the value for I1? It's so laggy. Shoot. Okay. I'm sorry. Is it worse than when I'm at home? 4. Okay. 4 is the correct answer, Feldmarsh. So we can talk about this, but it seems like this is not working as well as when I'm at home. So sorry about that. 4 amperes is correct. Good. 4. Okay. Good. Anessa, no, it's not worse than it is when I'm at home, or is it just at home is better? Okay. Good. Okay, so I1, just a reminder, we have Ohm's law, and Ohm's law says any I is equal to any V delta V divided by that resistance. That is Ohm's law. Click it up just a tad. There we go. So I1, good job, Isaiah. So I1, sorry, come on. There we go. I1 is delta V1 divided by R1. So if we plug in 12 volts divided by 3 ohms, we get 4 amperes as the current that passes on the left branch. I'm going to write it over here. A little bit weird, but that's where we're putting it. 4 amps in this branch right here. Okay? Good. Yes, 12 divided by 3 is correct. Let's take a look at the other side. Let's see what's going on the other side. On the other side, we'd like to know how much current flows over here as well. And let's call this I23. That makes sense because it goes through 2 and goes then through 3. Okay, so I23, how big is that current? Well, to figure that out, let's figure out how much resistance does the orange circuit have. We have 2 resistors in series over here, so our total resistance, R23, is the resistance of our 2 resistors together because they're in series. I'm going a little fast because we're short on time. Good job. I think that was Anessa, was it? It was Feldmarsh. Okay, as well. So this is 6 ohms over here. So our total resistance on orange, R23, is 6 ohms. Okay, so that means that I23, which is delta V23 divided by R23. Okay, well, that's equal to 12 volts divided by 6 ohms is equal to 2 amperes in that branch. It's not 2 volts, it's 2 amps. Okay, so 2 amperes flow here, and this is the last thing we're going to do, and then we'll be done. So we found 2 amps flowing over here, 4 amps flowing over here. Well, what is the total current then? Okay, we've got 4 amps here, 2 amps here. That means we had to have had 6 amps in total. Okay? For this to make sense. Good job, Anessa. Okay, we're at the end of class. So I hope that helped you understand better series and parallel circuits. And hopefully now that you're looking at the lab, it'll help you kind of guide you through. Okay, and my plan is to see you again next Monday at 9 o'clock. And I'll see you then. Bye.